Today, I have a half hour. I gotta get tires replaced on my car. So, the way I start every day, after I get my food, got a little bit of oatmeal here, a little bit of orange juice, is after I get that, go through routine. Before I start streaming and do any work, do a little bit of Brilliant.org. Not a sponsor, maybe one day. Started using Brilliant.org because of a lot of people who've promoted it, people that I respect. Um, so today I was like, hey, you know what I've been doing? Infinity. Cool. So I thought this would be a fun thing to do for a half hour. Usually I do Brilliant for about 15 minutes, but as you can see, I just got to level 3 of Infinity. I'm in the Neodymium League, which is, they just give you experience points for doing stuff, so let's just do a little bit of Infinity. It's fun. And I'm going to be eating a little bit here too, which is, also great. Just great for streaming. Mmm. Delicious. Delicious oatmeal. Mm-hmm. The instant stuff, the good stuff. So we're going to zoom in a little bit, just so you guys can see real good. Okay. So what we're starting with today is infinite areas. So we've already, in the past 2 lessons, which I think I've done, or the past 2, series of Infinity, some of the big things about Infinity. I was a math major, so did a lot of Infinity, a lot of calculus. One big thing that they went over is infinite sets. So a lot of it was set theory. So we're talking about learning how sets can be infinite. The big thing this is like 3 and 2. It was learning about like Cantor's theory. Who is Cantor? How can 2 different types of infinities be different sizes, which is called the cardinality. They even got into the power set and how the cardinality of the power set is greater than the set itself. Really cool stuff. Here it looks like we're going to be talking about infinite area, and then what was it, the other one? Infinite circumference, maybe? When I was... One second. When I was in middle school, I remember doing geometry. And, this symbol comes up a lot because it's a simple thing. You're putting an equilateral triangle inside 3 other triangles. I just couldn't help myself. I was in the middle of playing Zelda or something. I still play Zelda. If you've seen OOT is my favorite game. I just was like, it's a Triforce. All the kids in the classroom, there was probably like a few who understood what I was saying. Where it's like, but like, you get that really awkward pause. Don't regret it. So here we have a Triforce and a Triforce and a Triforce and a Triforce. So, infinite areas. We start with an equilateral triangle. Connect the midpoints of each side and divide it into 4 smaller equilateral triangles and shade the middle one blue, leaving the others blank. You repeat the same process with the top smaller triangle and so on indefinitely. So I also did some math problems for a while, and some of them had this idea of estimating, okay, well, what percentage of the shaded area is the whole thing? I bet part of this infinite areas is going to be talking about limits, which is another big part of calculus and infinity, but we'll see. So there you go. What fraction of this large triangle is shaded blue? Now we know that if we just ignored this extra stuff, it could be 1/4. And if you look at it, we're doing 1/4 plus 1/4 of a quarter 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 to n. So it's definitely not 2/3, it's definitely not 3/4, it's 1/3. And that's because this area is approaching 1/3. And we'll be talking about that, I'm sure. So it says, in the previous answer, we showed that the triangle is made up of progressively smaller trapezoids. all of which have a third shaded blue, which means that the entire triangle is a third blue. Wait a second. Trapezoids? I wasn't looking at it in trapezoids. Smart. So they ignored the top part and said, well, this is a third, and then that's a third. And as you keep going up, you get a third, a third, a third, a third, a third. That's neat. This approach divides the picture into progressively smaller trapezoids. We can take a slightly different approach, thinking in terms of triangles rather than trapezoids. Take the entire triangle figure and shade part of it permanently, leaving the triangular portion unshaded, and then repeat the process with the unshaded portion. This is kind of what we were doing a little bit. For this problem, we color the middle triangle blue and color the two triangles on either side yellow. The triangle on top is left empty because it will be divided into 4 triangles in the next stage. Altogether, after repeating the process infinitely many times, the large triangle will be completely shaded blue and yellow. For every one blue triangle, there are 2 yellows. So again, we see that the large triangle is a third blue. So it's again a way of reinforcing this idea that as you keep going, you're getting a third, a third, a third, a third, a third, a third, and eventually it fills up. Another cool way of thinking about it is starting with a square, and it's doing the same idea. Is you're taking the top right corner and you're repeating an algorithm of shading in 3/4 of it. So here it says, here we start with a square and divide it into 4 smaller squares, shading all but the top right. Then that square is divided into 4 smaller squares, and we shade all but the top right. We repeat the same process with the top right square indefinitely. If we continue on with this process, what fraction of the large square will end up being shaded? And this is heading towards 1. So as you can see, as it gets smaller and smaller and smaller, the infinity is heading towards 1. And I'm sure they'll get into limits at some point. In this one, we start with a square and divide it into thirds vertically, shading the left third yellow and leaving the others blank. Then we take the middle third and divide it into thirds horizontally, shading the bottom third and leaving the others blank. We repeat this process, alternating vertical and horizontal divisions indefinitely. So that's a little bit weirder, but clearly it's heading towards half. So what fraction is this yellow? It's a half. The previous problem could be thought of as a sum of an infinite number of fractions. So now we're talking about infinite sums, which is another big part of learning about infinity and calculus. In the first step, we shade a third of the figure. In the second step, we shade a third of the third of the figure, and so on. And each step, we shade a third of what was shaded in the previous step, continuing on indefinitely, or infinitely. The total fraction of the figure is shaded by this fraction. And as we saw, the sum is 1/2. So as you keep adding this stuff up, you can see that it keeps approaching 1/2. We won the lesson! Woohoo! Whoa, look at us! Streak extended. Alright, so we started off with infinite areas. Now let's go into infinite sums. And this level is fractals and infinite sums. What I did over the prior couple weeks, this is what I do prior to streaming again, just on my own, is we did sizes of infinity. This is all about sets. What is cardinality? The cardinality is the infinity size, things being more infinite or denser than other sets. We talked about Cantor, and at the very beginning, it just kind of introduces infinity. So let's go to infinite sums. Gotta take another bite of oatmeal before this turns completely cold. Infinite sums. Consider a square with area 1 and this procedure. So area 1 means it's a 1x1 square, unit square. Divide the 4 squares into equal areas, which I did here. Color the top left of these squares yellow, the bottom left blue, and the bottom right red, leaving the top right empty. Repeat these 2 steps, 1 and 2. So this is exactly what we had previously in the other lesson, but now we're using different colors. Below we see the result of this procedure left and the result after repeating the procedure. There will always be a blank square, theoretically, so we can proceed this procedure ad infinitum. If we repeat the procedure one more time, what's the total area that's shaded blue? So we did 1/4 plus 1/16 plus 1/64. It's this. If we continue to divide and color the blank square, after repeating the procedure infinitely many times, the square will be colored in completely. Which equation represents the total area of the square that's colored blue? So it's 1/14, 1/16, 1/64, 1/256, all the way to 1/2. No, 1/3. Sorry, I was just reading the first part. I didn't read the second part. Just kidding. I didn't read the app. No one saw that. We have shown that the sum of infinitely many terms can be finite. It's kind of a big deal. It's like a limit. In the introduction, we learned about Zeno's paradox, did we? Sure. Achilles wishes to travel some distance, say 100 meters. In order to reach his destination... Oh. This was like a bunch of lessons ago. In order to reach his destination, he must first make it halfway there, 50 meters. Before he can get halfway there, he must first make it a quarter of the way there, 25 meters. Before that, 1/8 of the way, 1/16, and so on. Zeno argued that Achilles would not be able to reach his destination because there was always a smaller half distance he had to cover first. So you're getting like, say you have 2 points and you're getting like this. You're doing half, 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 half. And I think they're going to continue that with this next one that we talked about. Each yellow shaded portion represents a fraction that is part of the sum. So you can see this one is doing like a cool little algorithm going up to the left. This one is doing a spiral. This one is doing triangles that are going inside each other like this. This one is doing a circle with a half shade circled in and then doing 1 and 1 and 1. Which diagram makes the counter argument that Achilles will actually complete his journey of half distances? That is, which of these diagrams represents the infinite sum that approaches, basically, or is equal to 1? So which one is chopping these in half as we approach? Well, this one, the first thing that you do is you're shading in this. This is half. And then you're doing half. And then you're doing half. So this one is approaching 1/2. This one's approaching 1. This one's approaching 1. This one's doing half. But then you can see this is not... Well, is this half? You're doing a consecutive... I think it's just B. It could also be D. I think it's just B. Oh no, B and D are a thing. Alright, it's gotta be B and D. I know it's B. I'm not sure about D. What? None? What? All of them? No, they don't. All of them? No, we're doing the halves. Oh, wait, he is approaching 1. It's approaching 1/2. It's A and C. Right. He's approaching the end. These were approaching 1/2. These are approaching 1. I got him flipped. Bad teacher. Hey, we win. The infinite sums we have seen so far have something in common. They're called geometric sums, where each term of the sum differs from the next by the same constant ratio. The first geometric sum had a quarter as the constant ratio, since each term was 1/4 times the previous term. So we had a quarter, 16, 64th. The second had a half as the constant ratio. Half, 1/4, 1/8. In general, we can visualize the geometric sum with 1 over n as the constant ratio. 1 over n plus 1 over n squared, etc. Where n is an integer, n greater than 1, in the same way using n equals 3 as an example. Like that. So here, n over 3. First split area into area 1 into n rectangular parts with equal area and color n minus 1 of them, like this. Each rectangle has an area of 1 over n. Next, split the blank rectangle into n square parts. So now we did that, now we're splitting into that. Each small square has an area of 1 over n squared. And this is yet another way of going to fill the whole thing. We can continue this procedure alternating between splitting the blank region into n rectangles and squares and coloring n minus 1 of them. With each step, the area of the single rectangle or square is 1 over n times the area of the previous square or rectangle. When we repeat this procedure infinitely many times, the original square becomes completely filled in with color. The infinite sum, 1 over n plus 1 over n squared plus 1 over n cubed, etc., represents the area covered by one of the n minus 1 colors. In other words, considering the whole to be one square unit, we divide this whole by n minus 1 to get the sum, leading to a formula of 1 over n minus 1. And as n approaches 1, you can see it's 1 divided by 0, which is, if it got to 0, it would be irrational, infinity. Calculate the value of the infinite sum. So now we got to do math. Take a little bite. Got 10 minutes left in the lesson. It's going too quick. Alright. So this is 9/10. So 9/10 plus 9/10 squared. All this. What is this approaching? So it's going to be greater than 9/10. I think it's approaching 1. Aha! We just showed that 0.99999 equals 1. This is a classic thing. 0.99 repeating is 1. The sum, it's the same as this. Then this is the same as this. And we just showed the former is equal to 1. We can also have alternating geometric sums where every other term is subtracted rather than added. So this is how we're approaching fractals. So here we have the bottom 3. Then you subtract half of it to make a trapezoid on these corners. Then you do this one in 3, and then you divide half, and you're kind of making these trapezoids as you go up. If the yellow regions represent area subtracted, which diagram represents the sum 1 minus a third plus 1/9? One minus a third plus 1/9. What the whole thing is 1. So you do minus a third, which is this whole thing. And then you add a 9th. A 9th would be this. So it would be B. We just saw these sums. 1 minus a third. Again, this is now area subtracted, yellow. 1 minus a third plus a 9th. 1 minus a third plus a 9th minus 1/27th. And we're kind of going plus minus plus minus. We can continue the pattern of alternating the addition and subtraction of powers of 1/3. In the subtraction stages, we take the centermost square and divide it into 9 squares of equal sizes, shading the bottom 3. This represents subtracting 1/3 of that center square's area. In the addition stages, we take the outer 2 shaded squares from the previous subtraction stage and instead only shade half of them. This represents adding 1/9 of that center square's area back into the previous sum. This is what, like, you doodle in your books and you're drawing like some stick figure and, you know, some other cartoons, and then someone in there is drawing infinite sums in the side of their notebook. There you go, look at that. Woo, cool. And then they did it even further. Look it's approaching a triangle. Neat. Even it does a little zoomy. If we continue the procedure forever, find the value of the infinite sum. What is the area of the white portion? If we subtract the yellow, well, you can see this is approaching 1/4 of the whole thing. So it's 3/4. Consider the following infinite sum, which isn't geometric. 1 plus 1/2 plus 1/3 plus 1/4. What is the value of this sum? So we're constantly adding a half. Then we add a third to that. So how many would this be if you combined all this stuff together? Well, you'd have to do sixths. So this would be 3/6, 2/6. So it's 5/6. Then you're adding a quarter. And a quarter is, well, what if you did twelfths? 6 twelfths. And then a quarter of that is 3/12, so it's 9/12. And a third of that is 4/12. So you're already at 13/12 here. So you've already gone past 2. I want to say it increases infinitely, but there's a certain point where it increases, like, it stops increasing, right? It's one of these two. It's not 100. I don't see no reason why it's 5 halves. I'm gonna do this, but I think it's 5 halves. But it could be that. I think it's 5 halves. No! No, I was right. Consider this diagram, which represents the sum 1/4 plus 2/8 plus 3/16 plus 4/32, where each term is of the form n over 2 to the n plus 1, which is what this is. So you can see we're adding, well, that's not easy to draw. What does the diagram suggest about the infinite sum? It says the sum is less than 1. The sum is greater than 1. Exactly. It's like approaching it, right? You can see kind of a filling in. By repeating an infinite sum geometrically, we can see that it's infinite, or we can determine its finite value. In every example we've considered, the terms of the sum get closer and closer to 0 the farther we go. This is a requirement for an infinite sum to have a finite value, but it isn't a guarantee of a finite value. When every term is of the form 1 over n, the terms get closer to 0 as n increases. As we saw, the sum increases infinitely. We can represent this with an infinity sign on the right-hand side. Oh, because like this is like a little bit more than that. And you can add up all these. Yeah, that would help me think about it. In a previous lesson, we found it to be infinite by comparing it to the smaller sum, 1 plus 1/2 plus 1/2 plus 1/2. The terms of this sum don't get closer to 0 as the n increases. Rather, they stay at 1/2 forever. Because the terms don't get closer to 0, we know that this sum is infinite. So here, 1/3 plus 1/4 is greater than a half. All of these terms together is greater than a half. And you can just keep going and going and going and going forever. And keep doing that. So my instinct was right. 180 XP. Grace. We did it! I gotta go. Oh, that wasn't quite 30 minutes. Well, that's too bad. It's been 25 minutes. Infinity. Infinity. So anyway, it's going to talk about snowflakes and fractals, and then we're done. Infinity's pretty short. But anywho, this is brilliant.org. It's really cool. When I very first started streaming, I was like I thought I was gonna start with this every stream. Because some of the early stuff I was doing was like cool engineering and, you know, stuff that was very intuitive as I was learning. And then I just dove straight into calculus. I thought I'll, like, you know, teach some foundations of calculus. Like, oh, it'll be too bad. And it's like, no, you got to get out pen and paper and really start writing, buddy. So I got algebra on here, programming computer science, which is great, data analysis. I did a lot of the science ones because that's the stuff that I don't know as much about, and wanted to delve into. Quantum computing was very, very cool. Some logical stuff. A lot of this logical reasoning is, of course, incorporated in other parts. Everyday math, if you want to just do some simple stuff. Technology. Some of this stuff's just grouped with scientific thinking. Then we have the advanced math. Oops, shouldn't have done calculus. Mind-bending math. I did all the math puzzles. Those were good. Right now we're doing infinity. And it's funny how it says mind-bending, but like number theory, that's just a course. So it's interesting that number theory is mind-bending, and that's the whole thing. So brilliant.org, super great. Not a sponsor yet. Maybe way down the line. If they wanted to sponsor a voice acting sketch video game channel. But anywho, that's it for today. We did some Infinity. Thanks for tuning in. Wait, we gotta end on Infinity. What are we doing? Go back. There it is. On Monday, we'll be diving back into probably some game dev or testing. But hey, just a little bit each day. One of the things I was thinking about some of these days when I don't have a full time to stream is when I was writing a novel. And, you know, at some point I'll probably, I will definitely do an audiobook of it and post that. It's on Amazon. It's called Rise of Rubin. And as I was writing, there are certain days where, you know, you're trying to continually make progress when you're writing something big or working on any project. And one of the encouraging things that someone said was, you don't need to spend like an hour or 2 hours, like a really long chunk, to make progress on something. Sometimes we have this idea in our mind that, oh, I need like to really carve out some time. And I think our phones and our people's shorter attention spans actually are training them to be like, you know what? If you just did 10 good minutes, if you just did 20 good minutes, if you wrote one paragraph, that's progress. So just finding a little bit of time. Same applies to prayer, same applies to a lot of other spiritual disciplines or anything that you're trying to find time in your day to do. So sometimes that's streaming. Sometimes you only have a half hour and you learn about infinite areas and sums. So anyway, that'll be it for today. Thanks for all tuned in on Twitch and YouTube. Check this out later. As always, love you guys. Jesus loves you too. Catch you on Monday.